Hello everyone, welcome back to the NPTEL course on materials informatics. In this lecture we will be looking at ensemble models and dimensionality reduction tools. Alright, so let us have a brief recap of what we discussed in the last set of lectures. So we looked at logistic regression and softmax regression. These are examples of classification models. K nearest neighbors which can do both regression and classification tasks, and it is a very important example of a instance based learning. We also looked at support vector machines and decision trees. These are quite powerful classical tools that we have that can do both regression and classification tasks, and we also looked at a few set of new hyperparameters associated with these models, right. So in this lecture we will look at slightly more complicated classical models which are referred to as ensemble models, and we will also look at examples of how to reduce dimensionality. Right, especially with the number of features that we may have to deal with in constructing practical machine learning problems. As before, all the schematics that I will be using, unless otherwise mentioned, are from this book by Aurélien Geron. Alright. So what are ensemble models, right? So far we have looked at machine learning models which work alone, right. So if you think about a linear regression model, we create one model that tries to make predictions on whatever target data we have, right. Same thing with support vector machines, same thing with K nearest neighbors, same thing with decision trees and so on, right. So ensemble models are slightly different in the sense that we now have a group of models which give aggregated answers or some kind of averaged answers, and these answers tend to be better than that of a single expert, right. And why are these better? Because they use what is referred to as the wisdom of the crowd, right. So let us say you have you want to do a classification task, and then you have a decision tree, one decision tree model which can which only has an accuracy of about 51%. So it is slightly better than a random model, right, a model that gives a random chance, right. But now if you have 10 different models, all of which are slightly better than average, so they all have 51% chance of making a prediction, making a right prediction, and if you start aggregating those predictions of all the different models and have some kind of a majority voting, right, then it is very likely that in the majority of the cases the models all the models sort of agree on the right classification, and only a few models do not classify the underlying task precisely. So what I mean by that is, so let us say you have a data point here, right, and you want to make predictions with 4 different models, right, and let us say each of these 4 different models are not particularly accurate, right. So they can let us say they only have about 60% accuracy compared to a perfect model which should have close to 100% accuracy, right. So let us say one model each of these 4 models when used individually may not give you a high degree of confidence that you are actually classifying this data point correctly, right. But let us say 3 out of the 4 models are classifying this new instance to be 1, and only one model is differing by 2, and let us say you are taking a majority vote. So you are looking at okay, so you are saying 3 out of the 4 models are voting for 1 or classifying it as 1, and hence I am going to classify the overall output as 1, right. So if you take an ensemble prediction like this, you actually have a much better chance of getting the right predictions or right classifications compared to relying on single models, right. One can also think of this in the case of in a more mathematical example, which is the example of a biased coin toss, right. So in general, if we have a regular coin, we have 50% chance of it landing on the head and 50% chance of it landing on a tail, right. So now if we have a biased coin, let us say which has 51% probability, so it is slightly more than random chance. So if you do 100 coin tosses, you are going to get 51 heads and 49 tails, right. So let us say you have this biased coin toss, and the thing that you want to predict is the probability of getting a head, right, over a certain number of tosses, right. So if you were to toss the coin 1000 times, right, then most likely you will get about 510 heads and 490 tails, right. But there are also instances where the biasing is not working perfectly and you end up getting 500 heads and 500 tails, right. So if you actually end up doing the math, the probability of getting a majority of heads is about 75% if you do 1000 tosses, right. Now if you were to increase that number to 10,000 tosses, right, so you take the same coin, do 10,000 tosses, then the probability of getting a majority of heads is actually 97%, right. So in other words, as you increase the number of tosses to a higher and higher number, you actually start approaching this 51% probability more and more, which implies that the probability of head being in the majority compared to tails will start approaching 100, right. So even though individual coin toss only has a probability of 51%, okay, being 51% that it lands on the head, so slightly more than random chance that it lands on the head. When you increase the number of tosses to a very high number, you are almost guaranteed to get the majority to be heads, right, and the tails will always be a minority, right. So this is in some sense how ensemble models work, right. So individual models do not have very good credentials, so they may not be a very great classifier, but if you agglomerate a large number of them, a large number of these individual models, then the final classification task, which is whether you want a head majority or a tail majority, becomes that much easier to estimate, right. So this in short is how wisdom of the crowd works, or how ensemble models work. And there are two ways of creating ensemble models. So one is you have the same data set and then you create independent models, right. So let's say you have 1000 data points, you create one decision tree model, one support vector machine model, one linear regression model, one logistic regression model, and so on. So you create 10 different models or 20 different models with different hyperparameters and so on, and you ask each of those models to make a prediction, and you take an aggregate of those predictions. So that is one way of creating an ensemble model, but this is not very common. The other way of creating an ensemble model is you have the same model, but you create multiple copies or multiple samples of your data, and hence create and train independent models, right. So you divide your data into multiple subsets or subsamples, and you create independent models that have only seen subsets of your data, and you take aggregate predictions of those models. So that is actually more common, right. And one thing to keep in mind is that this wisdom of the crowd or ensemble models work fairly well when the models themselves are fairly diverse. So in other words, there is no correlation between two different models, and there should be a sufficient number of models as well, right. So what do I mean by correlation, right. So if you want to train let's say decision trees, right, and then you train 10 different decision trees, so 10 identical models on the same data set, on the same let's say 1000 data points or 100 data points, right, then there won't be any difference between the predictions of your 10 models, right. So in other words, the predictions of all the 10 models are highly correlated, right. So there is no wisdom of the crowd there. So for any new classification task, all the 10 models will give you identical predictions, right. But if you were to split the 1000 data points into 10 different subsets, so 100 data point sets, right, and you create 10 different models, then each model knows something about a subset of the data, but not about the full data set itself. So it will give you fairly different predictions. So each model will give its own predictions for a new data set, and the predictions of each model will actually not be correlated. Right. So that is what we want actually. So if the predictions are not correlated, then the aggregation of the predictions actually gives us a much better prediction than training one decision tree on the entire 1000 data point data set, right. So we want to create models that are fairly diverse, so basically do not have any correlation. And the ensemble model should also have models that a sufficient number of models within them, right. So if you have an ensemble model of let's say support vector machines and you only have 2 models, right, then you are relying on 2 votes, right, or 2 predictions to make an aggregate prediction, which may not be sufficient compared to let's say you have 100 support vector machine models and you are taking the aggregate of those 100 models. That is guaranteed to give you much better predictions than having just 2 support vector machine models, right. So in general, when we create ensemble models, we should create a as diverse models as possible. So models that sort of see different pieces of the data or non-correlated pieces of the data, and we should try to create sufficient number of models so that the aggregation actually makes sense, right. So that the aggregated predictions are much better than the individual predictions. Okay. So with respect to ensemble models itself and ensemble models that actually learn on individual slices of the data. So we are trying to train the same model but on different slices of the data. There are two strategies that we can actually adopt. One is referred to as bagging and the other is referred to as pasting, right. So what is bagging? Bagging is short for bootstrap aggregating. And here the sampling of your full data set is actually done with replacement. So what I mean by that is, so let us say you have a set of 100 data points and you want to create models that are training on 20 data points. So 20 data point subsets of your 100 data points, right. So let us say sample one data point out of your 100. Before you sample the second data point, you have a choice whether to replace the data point that you had sampled or not replace. So when you replace it, when you are sampling the data set again, you have a chance of getting the same data point again, right, in your subsample, in your subset of 20 data points, right. If you do not replace, then you do not have the chance of getting or sampling the same data point again, right. So if you do replacement, so if you start off with 100 data points and if you want to create a 20 data point subset, if you do replacement after sampling every data point, so basically you always have 100 data points to sample, right, for any of the 20 data points. So you sample the first one, you put it back, and then you sample the second one, you put it back again, you sample the third one, you put it back again, right. So you always replace it, and if you create subsets of data by doing this kind of replacement, that is referred to as bootstrap aggregating or bagging, right. So the key takeaway message is that in bagging the same training instance or the same data point can be sampled multiple times for the same model, right. So this is possible, and sometimes this does not really hurt the model or hurt the ensemble itself. But the key thing to note is, since we do replacement, right, the probability of sampling one data point, right, is always a constant, right. So let us say you have 100 data points, you sample one data point, you then replace it back, the probability that you sample that data point again is 1 over 100, right. So whenever you create subsets of your data points, since the probabilities of sampling do not change, you basically get fairly independent sampling of your data points themselves, right. So bagging is actually quite nice in the sense that whenever you sample, all the data sets in general will not be very correlated, right. So the data points themselves will be fairly independent, right. Pasting is the opposite of bagging, where your sampling is actually done without replacement, right. So once again, if you take the 100 data point sample, you want to create a 20 data point subset, right. You sample the first data point, you do not replace it back, so now your overall data set now becomes 99, right, it's no longer 100. You sample the second data point, it becomes 98, you sample the third data point, it becomes 97, and so on. So you see that the probability of sampling data points keeps changing as you sample more and more data points, right. So that is what pasting does. So here the same training instance can only be sampled across multiple models. So the same model will only have will only be able to sample one data point once, right. So it won't have the chance to sample the same data point multiple times. The probabilities can be correlated because when you take one data point, right. So let us say you had 100 data points initially, you have already sampled one, you are left with 99. Now the probability that you sample any of the remaining data points is 1 over 99, not 1 over 100 anymore, right. So the probabilities of sampling tend to have this correlation built in, right, and hence they are not truly independent sampling of your data set itself, right. But the nice thing about pasting is that every model will always get significant diversity in how it samples the data. So in other words, since the same data point cannot be sampled multiple times in a given model, each model is fairly diverse by itself, right. So the sort of one thing to keep in mind is that generally when you use pasting as a strategy, it generally creates higher variance. So the tendency for overfitting becomes higher compared to bagging. So bagging is a better way to regularize your model compared to pasting, right. And in general for ensemble models, bagging is quite commonly used, and almost always for ensemble models you will have this hyperparameter called bootstrap. So if you set bootstrap equals true, you are using bagging, right, you are using bootstrap aggregating. Okay. So that is one thing to note about ensemble models. The other thing to note is how you are actually sampling, right. So whether you are sampling a subset of features or you are sampling a subset of instances, right. So we have already concluded that most ensemble models are created by sampling a subset of instances within your overall data set itself, right. But you can also sample a subset of features, right. So let us say you want to create a decision tree model again, and you have access to 100 features, right. So you can say that for each decision tree each tree can only use a maximum of 10 features and not all of the 100, right. So if you were to restrict the number of features being used right in the creation of individual models, then that is referred to as random subspaces, right. So here you sample a subset of features within each model, and this is sort of equivalent to training different models, because if you train with different sets of features then the models themselves are sort of different. And the hyperparameter to use for subsampling features is using this max features hyperparameter. So that is random subspaces. Random patches basically includes random subspaces with instance sampling, right. So you sample subsets of both training data of your instances as well as features, right. So in general random patches is the strategy that is commonly adopted right for ensemble models, right. So one thing to keep in mind is in general when you sample subsets of feature spaces, right, so you use random subspaces or random patches, it generally lowers your variance and increases your bias. So in other words it is a way to regularize your model, right. So random patches keep in mind is generally the most commonly used, but you can also use just random subspaces and not take into account any sort of instance sampling. Okay. So what is one very common example of an ensemble model? The most common example is actually random forest. The random forest model is basically an ensemble of decision trees, right. So how are these decision trees trained? They are generally trained via bootstrap aggregating or bagging, right. You do employ random patches, so you sample a subset of your data points and you also sample a subset of your features. And once trained, the random forest can be used for both regression and classification tasks, right. So I will give an example of how random forest can really make a difference, right. So let us say this is an example of a decision tree. You have two distributions of data points here, sets of circles and sets of squares here. So if you use a singular decision tree and if you want a very good classification of these two collections of data, you see that you may have to result in a very complicated decision tree with a lot of depth and lot of branches as well, right. But if you were to use random forest, so this is basically decision trees with bagging, you see that the sort of the decision thresholds, right, you can get a fairly smoother function of the decision thresholds and a simpler function as well compared to the non-trivial perpendicular splits of data that we have here, right. So you can get a fairly smooth set of classification or decision thresholds which helps you classify your circles from squares much more efficiently than the case here, right. So this is an example of just a decision tree model, this is an example of a random forest model, and you can see that random forest model can give you much better classification compared to a decision tree model. Okay. So how do you actually use random forest? From scikit-learn you have this ensemble module, and from there you can use you can import either the classification model, so which is random forest classifier, or the random forest regressor model. and as you would expect, right, so we are sort of going higher in terms of complexity, and the more complex our models get, the more hyperparameters that we will have to worry about, right. So in the case of ensemble models, you will have 4 different sets of hyperparameters that you will have to worry about, that you will have to optimize and tune. One is the hyperparameter associated with the ensemble itself, right, and in the case of random forests, that the simplest one is, how many decision trees do you actually use, right. So how many models do you actually train within your ensemble to get an aggregated prediction, right. And that is your n estimators hyperparameter. This is a very important hyperparameter for any random forest model, right. So how many decision trees do you consider in your forest, right. So that is in the ensemble model itself. Second is the sampling method, right. So how do you actually sample your data points as well as your features, right. So the one parameter that is often used is max samples. So max samples basically indicates how many samples any given decision tree would be trained upon within your overall data set, right. You can also consider max features as an additional hyperparameter here, right. So that is the sampling methods itself. Apart from these two, you also have hyperparameters associated with each individual model, right. So remember that ensemble models are a collection of individual models. So random forest is a collection of decision trees, right. So you have hyperparameters associated with the random forest. So how many trees does it have, and how is it going to sample for each tree, how is it going to sample the number of features as well as the number of data points that it has, right. So that is at the ensemble level, but for each tree you also need to specify its own hyperparameters, right. That could be the maximum sets of hyperparameters that we saw in the previous lecture, or it could be the minimum set of hyperparameters, right. So one example is maximum leaf nodes. So how many leaf nodes should you have per decision tree, right. So individual models will also have their own hyperparameters that we will have to optimize, and then any hyperparameters associated with the algorithm itself, right. So in the case of support vector machine, for example, so if you are creating an ensemble of support vector machine models, we'll have to probably mention an epsilon hyperparameter as well for regression tasks, right, and for classification tasks we will probably mention a C hyperparameter, right. So this is specific to the algorithm that we are using to fit the model itself. So whenever we consider ensemble models, we have to worry about these 4 levels of hyperparameters, and we will probably have to fine tune all the 4 levels, right. So which means our grid search cross validation or random search cross validation will become quite expensive to tune all the hyperparameters for these ensemble models. Okay. One very common strategy that is often used for regularization, especially when it comes to ensemble models, is early stopping, right. So as I mentioned in my previous slide, we have lots of hyperparameters to worry about for our ensemble models, which means if we actually tune individual hyperparameters, right, using grid search CV or randomized search CV, it's going to take a lot of time, right. So the key thing is now to identify some hyperparameters that are very influential and use early stopping as a way to identify what is the optimal amount of those hyperparameters in a faster or more efficient fashion, right. So let me give an example, right. So let us say you have a regression task here where you are trying to get this target y values as a function of your x1 features, and let us say you are trying to construct a random forest model with three decision trees. So the number of models with that are giving individual predictions to your aggregated model itself is 3, right. So if you only have 3 estimators, you see that the model is fairly underfit, it's not getting the parabola as smoothly as you would like, right. But if you now use a very large number of trees, right, so number of estimators is 200 here, so that is a large forest, right. You see that the model almost gets every single data point correctly. So in other words, the model is actually overfitting, right. So we see that number of trees or n estimators is a very important hyperparameter, right, in our random forest model. So we can actually track the validation errors or validation or test errors, right. So in general you should use validation sets for tracking these errors here. So if you use validation errors as a function of number of trees, you can then try to identify at what point you reach the minimum in terms of your validation error, and that basically gives you your early stopping criterion or your most optimal sets of number of estimators or number of trees here. So if you do this exercise for this simple regression problem, we see that the best trees, the best model or the most optimal model is with 56 trees, right. So if we use 56 trees, we are roughly recovering the roughly parabolic nature of our data points here, right. So early stopping on the validation set is almost always used in ensemble models, especially random forests, to identify the optimal models. Okay. Another fairly important thing that is that comes up with random forest is the importance of different features, right. So in other words, so let us say you have a collection of features that are contributing to your overall model, so to your overall predictions, and you want to understand the importance of some features with respect to other features, right. You can actually create these kinds of very nice heat maps, right. So basically darker pixels here indicate features that are not very important, and lighter features indicate features that are very important. So with random forest, since you can sort of trace the aggregation of the predictions, so you are getting an aggregation of predictions from different decision trees, which implies you can trace the importance of a given feature on the final predictions, on the final aggregated predictions based on how it contributes to different if else decisions, right. So this is something that can be readily calculated with random forest models, and the basic thing to note is that the sum of all importances is will be equal to 1. So if you add up all the importances here for all the features, that should come up to 1. So these are all normalized importances, and we can try to identify the important set of features very quickly using a random forest model. And this is often used to fine tune or to get lighter models. So you create a random forest model, you identify important features, and then you use those subset of features to now create a better model, maybe a better random forest model or a better decision tree model or a support vector machine model and so on, right. So feature importance is something that sort of comes up fairly straightforward from random forest models, and this can also be calculated fairly easily with scikit-learn. Okay. So with that we move on to what is referred to as sequential learning. So in ensemble models there are two ways that you can actually learn. So one is what is referred to as simultaneous learning. So we create all the weak models at once, ask them to make predictions right at once, and then we take the aggregation of those predictions, right. And that is how typical random forests work, right. So that is referred to as simultaneous learning. So for a given data set, you split the data set into multiple subsets, you train all the weak models at once, and then you aggregate all the models at once, and then we make aggregated predictions, right. The other way to learn instead of simultaneous learning is what is referred to as sequential learning, right. So here also you try to create an ensemble model, right. So you try to create a collection of weak predictors, right, but the collection is made sequentially, right. So you first train one model on your data set, and then you add a second model which is designed to make the predictions of the first model better, right. So second model is second model when you add up to the first model becomes slightly better than the first model by itself, and then you create a third model which becomes better than the first two models combined, and you create a fourth model that becomes better than the first three models combined, and so on, right. So if you create or if you sort of learn in a stepwise manner, you create weak models in a stepwise manner, and you design them such that each weak model is better than its predecessor, that is referred to as sequential learning, right. So simultaneous learning is train all the models at once and you make an aggregated prediction. Sequential learning is you train models in a stepwise manner where every successor model is trying to be better than the previous model, than its predecessor, right. So sequential learning is another way to create ensemble models, and there are two popular methods by which we can create sequentially learned models. So one is referred to as AdaBoost or adaptive boosting, and the second is referred to as gradient boosting, right. One thing to keep in mind is that sequential learning cannot be parallelized. So model learning will be fairly slow. Right. So, random forest by itself or random forests or simultaneously learning models are by themselves fairly slow, right, because you have lots of hyperparameters that you would need to tune, and at any given instance of time, it's a random forest is trying to train several decision trees in one go, right. So, random forests by themselves are fairly slow, but at least the training of the individual models. So, let us say your random forest has 100 different decision trees, each decision tree can be trained in parallel, right. So, if you have enough computing resources, you can actually train all those decision trees in parallel, and you can actually improve the speed of your speed of training of your random forest model. But in sequential models, that parallelization is just not possible, it is not possible by design, right. So, each decision tree has to be trained only after its predecessor has trained completely and is ready to make predictions, right. So, sequential learning cannot be parallelized, which implies that the training process of the models can be fairly slow, right. But the trade off is that in general sequential learned models can be much better compared to, or much better or much more robust, much more accurate compared to simultaneous learning models, right. So, on that note, we will stop this lecture. So, just as a recap, we looked at ensemble models, the importance of wisdom of the crowd, and how splitting of data and splitting of features can result in fairly powerful ensemble models. We started touching upon sequential learning. We have not finished sequential learning yet. So, in the next lecture, which will be a continuation of this lecture, we will cover sequential learning in more depth, and we will also look at some models that can be used for dimensionality reduction exercises. So, with that, I thank you all for joining today. I will see you all in the next lecture.